I'm going to talk a little bit about the work that I've been doing the last year on adding pattern matching to the Java language, although very little of this talk is about the language. It's mostly about the language runtime, which I hope will be usable by languages other than Java as well. So you've all seen this slide a bunch of times. That's how you know I work for Oracle. So, okay, what's pattern matching? A lot of languages feature pattern matching, which is a primitive for test and destructure. You have some target that you want to match against, and a pattern match combines, does it have the characteristics you want, with, if so, extract the bits of state that are interesting to you. And this is a feature that we've seen in languages going back probably 40 years. So languages that were designed around text processing, like Snowball, supported pattern matching on strings. It's something you see very commonly in functional languages. So if you're a functional language that has structural types like tuples and sequences, you will say things like, does this match a tuple of A and B? And if it's a tuple, it binds A to the first part and B to the second part. Or does this match a sequence of A, B, C? And if so, it'll bind A, B, and C to the first, second, and third elements of the sequence. You also see pattern matching in functional languages that have nominal data types. So Haskell data classes, which have the names the types have names and the components have names. You can say, is this a pair of X and Y? And if it's a pair, it will bind X and Y to the first and second element. And if you use Scala calls these case classes basically the same thing. So this is a feature that has shown up in a lot of different languages, and it's also something that is being added to a lot of other languages, not just Java, but C# has pattern matching in the most recent version as well. So this is a feature that's not just a functional language feature. It fits very nicely into object-oriented languages. And so, if we're interested in adding pattern matching to Java, the first question we ask, in addition to, how do we make it work, is, are there pieces of it that are not Java-specific that other JVM languages would be interested in using as well? So most of this talk is about features in the JDK libraries that can be used by a compiler to target, to make it easier to do pattern matching. So if you haven't seen it, I'll go through a few examples. If you have seen it, I apologize for the redundancy. But a pattern match combines, as I said, an applicability test. Do you match this pattern? With a destructuring bind. Get little bits out of the target and bind them to new variables. And this is something we do in programs all the time. And in fact, it's in Java, it's quite repetitive. The way a pattern match might look in Java is maybe we'll have a predicate called matches, and we'll say if this thing matches this pattern. And the pattern that we show here is a destructuring pattern. The applicability test is, are you a point? And so it'll do an instance of under the hood. And if you are a point, it'll go and get the X and Y field out of that point and bind them to the new local variables X and Y. And then you can use X and Y in the code that follows. And the thing evaluates to a Boolean, so if it doesn't match, obviously nothing gets extracted and you move on. Now, we could do this today in Java, of course. What would we do? We'd say, if X instance of point, and then if that succeeded, we would cast X to a point. So X as point equals point X, and then we would extract the fields, X as point.x and X as point.y, which we do all the time, and yuck, right? I mean, I just asked you if an instance of, and the next thing I have to do is a cast. Well, what else would I do after an instance of, right? In some sense, this is syntactic convenience, but there's also a lot more to it. One of the interesting new things that comes out of this, and this is not something we've had in Java before, is an expression that produces new variable bindings as a sort of linguistic side effect. Right, that the variables, the binding variables X and Y in this example, they're not declared in the enclosing scope. They just spring into existence if the pattern matches, and that's kind of a new thing. Now, there's lots of really interesting language design questions here, like, what is the scope of these variables x and y? And we have interesting answers to those, but that's not the subject of this talk. So we're going to talk mostly about what does this mean for JVM language implementers. Okay, let's do a few more examples before we move on. So this is code that we've all written, where you have some object, all you know it's an object, and maybe it's an integer, maybe it's a string, maybe it's a float, because it came out of the JVM constant pool, so it's going to be one of those things. So the first thing you do is you do an instance of test, and if that succeeds, you cast it, and then you use it. And so we've all written this code because we all have to write this code, but like everything about this code sucks, right? So first of all, there's a lot of repetition and boilerplate and unnecessary coding, right? I just did an instance of test. Why do I have to cast it? Couldn't you figure that out for me, right? There's the business logic is sort of obscured by all the boilerplate of instance of and casting, so it's not even obvious what's going on. It's actually very easy to make a mistake, and if that mistake happens to be in a branch that isn't taken very often, then you might not notice that mistake, might not be caught in testing. It doesn't exploit definite assignment necessarily. Very often when you do something like this, you want to do exactly one thing in each of these arms, but the if-else-if is a very general language construct. So we're using an overly general language construct and hoping we get it right, and that's often a source of bugs. And it's also accidentally sequential, right? This code is going to be O of n, because absent like extraordinary heroics by the JIT, it's just going to march down the the list in the order that you wrote it. When in theory it should be O of 1. So we really hit the trifecta here, right? It's like verbose, error-prone, and slow. Woohoo! Okay, so we'd like to do better. So here is a step in the right direction. If we had our switch statement and it supported type test patterns, we could write it like this. So what's happening here in each case label, we're saying case integer I, that's a type test pattern. The applicability test is, are you an instance of integer? And the destructuring part is, well, cast it to an integer then, and bind that new integer to the fresh variable I in this example. So step in the right direction. We eliminated the pair of instance of cast and we fused it into a single operation. That's an improvement. It makes the code a little bit easier to read. And now that you can read the code, because some of the garbage has been taken away, what you see is I'm actually doing an assignment to this formatted result in every arm. And actually, I'd like the compiler to prove that it was going to do that for me, that I'm going to make that assignment exactly once. I want definite assignment to work for me. So really, what I want to do is turn switch into an expression, not a statement. So, and you can do this. This is pretty straightforward. So this is what it might look like if we allowed switch to also have an expression form. We get rid of the breaks, we get rid of the intermediate assignments, and now the compiler is working for you that says, well, it had better be one of these. There had better be an expression of the right type on the right-hand side of each one of these things, and at the end of this, it's going to have assigned one of those to formatted, right? So this is a much more compact representation of the same thing than we had 2 slides ago, and if the code is more readable, it's going to be harder to get wrong, right? So it's not that we can't write code like this in Java today. It's just the mechanisms we have guide us towards an overly verbose and error-prone and potentially poorly performing idiom. So let's fix that. Here's another example of how you might use pattern matching in a Java-like language. Imagine you have a tree, an expression represented by a tree. So you have expression nodes, which might be an add node or a multiply node or a negation node, and you want to evaluate the thing. So these are somewhat more sophisticated patterns. These are destructuring patterns, which not only combine the instance of test and the cast, but also reaching in, grabbing the fields, and binding them to new variables. So if you have something that is an add node of 2 other nodes, it'll take the left and right nodes, bind them to the local variables left and right, and then recursively call the evaluator to evaluate each subnode, add them together, and return that. So again, this is something we could do with a switch or a visitor, but it would be a lot more error prone. And with visitors, it would be, a page and a half of code, and you have the double dispatch, which, makes it harder to follow what's going on, and it's really easy to make a mistake. So this way, what you want to do is front and center. Code reads like the problem statement. One more example of how this might look is, supposing you want to take one of those expressions, you want to simplify them using a bunch of algebraic identities, like 0 times something is 0, and 1 times something is whatever you started with, and 0 plus something is whatever you started with. You could easily do this with visitors. Now we're at like 5 pages of visitor code. You can, fit this in one page on, with using patterns, where you're saying, okay, are you an int node? Okay, we're just going to pluck the integer value out of it. That's easy. Are you a negation node who the thing being negated is also a negation node? Patterns compose. So the thing, when I say case neg node, open paren neg node again, the thing on the inside is another pattern. What I'm saying is, are you a negation node? If so, extract the thing that you're in negation of and match it against the pattern neg node again, right? So if you want to say negative, negative something is just the something, this pattern will match that. And if you're negative of something else, it won't match that, and you'll move on to the next case, which is a more general case, which is negation of anything. Okay, so patterns compose really nicely, right? So this is the things that are inside the parentheses of a destructuring pattern themselves can be patterns, and in fact, like the one that says 0 plus something equals something is actually nested 3 deep. I'm saying, are you an add node whose left component matches int node of 0? Well, that's a pattern, and the 0 itself is a pattern. That's a constant pattern. Constant patterns only match the constant 0. So I can express something that would have taken 3 levels of if-then very compactly, and again, code looks like the problem statement, right? So just imagine how much fun this would be with visitors, right? So patterns are cool. There are multiple kinds of patterns that you can have: type test patterns, constant patterns, destructuring patterns, and they compose through nesting, which allows you to say what you want all in one go. So, okay, good feature, we like it. All right, how do we implement it? So, you can think of, you can think of this as being the complement of the kind of polymorphism that we get out of class inheritance, right? So, the polymorphism that we get in Java has to do with classes declare methods, classes get extended by other classes, and those classes can override methods from their supertypes. And then Java gives us dynamic dispatch on the receiver type, and so this polymorphism is encoded in our class hierarchy. And very often, that's exactly what we want. And in fact, in the example I gave before about node evaluation, we might very well have had an eval method on node, and the implementation of the eval method on add node would have been evaluate these 2 nodes and add them up and return that. That's a very sensible method to put on in your node hierarchy, but there's also operations that we tend to do on trees that aren't necessarily sensible to actually put in the hierarchy themselves, right? So, if I wanted to answer the question, do I have a subnode which evaluates to 42, that would be a stupid kind of thing to try to pollute my hierarchy with. Other languages approach polymorphism from the other direction, from the use site direction, where pattern matching is a way of simulating dynamic dispatch by saying, here are all the cases I care about in one place. And these 2 things complement each other. It's not like one is right and one is wrong. The declaration site approach makes a lot of sense when this is an operation that is intrinsic to your type hierarchy. There are operations that aren't intrinsic to the type hierarchy, but we still want to perform on a tree, which is usually when we reach for the visitor pattern today. So this is, serves all the purpose that a visitor pattern did, but with an awful lot less boilerplate, less error prone, and more optimizable. So I sort of see this like use site versus declaration site polymorphism as being complementary. They're not competitive. It's not that we want one or the other, or one is better than the other, but they're each good for, for different sorts of things. Okay. So if we think about this more abstractly, about how this fits into the object model, the examples of destructuring that I showed are the dual of construction, right? A constructor takes a bunch of arguments and produces an aggregate. So new point of 3, 4, I take the state of my point, 3, 4, I call the constructor, and it gives me a point that encapsulate that state. When I did a match against a point, I was doing the opposite of that. I'm taking the point and I'm exploding it back into its constituent parts. And while not all objects naturally support this kind of reversible construction, and in fact, for some objects, we don't want to provide reversible construction because we want to keep our state more tightly hidden. For a lot of objects, especially those that represent just ordinary data, it's very useful to be able to go back and forth between the state representation and the aggregated representation. So if we define, a destructuring match as the dual, the complement of construction, these things can work with each other, right? They compose pretty nicely. If I take an object, destructure it into its constructor arguments, and pass that back to the constructor, I can just compose these as functions, and that's basically a clone operation. If somewhere in the middle I destructure something, I encode it into some, XML, JSON, string, form, whatever, I pipe that into something that decodes the elements and back into the constructor. That's a serializer, right? So these two things work very naturally as complements as part of the object model. And I think that pattern matching fits much more deeply into object-oriented programming than a lot of people give it credit for. So our thesis is, this is part of the object model. Let's make it so. Let's make it possible to expose deconstruction as a first-class member. And deconstruction, just like construction, might entail arbitrary logic, but usually not. Usually it's pluck the fields out and move on with it. Okay, so the obvious question that we ask ourselves is, is this a language feature or a VM feature? Or more specifically, is there some part of this feature that we would really like to have VM help with? So if you think about how we process a method call today, there's two sides: the declaration and the use, and the mediation between the declaration of the use and the use is nominal dynamic linkage, right? So the call site says, here's the method and descriptor I want. The declaration says, I'm a method with this name and descriptor, and at the first call, the VM looks for the method, matches the parameters up, and links them. So we would like to be able to have that same kind of mediation for patterns when we do, say, does P match this, this deconstructor? We want that to go through the same overload resolution mechanism and dynamic dispatch mechanism as we do with methods. And they look a lot like methods. In fact, if you squint, they're almost like methods, except they're really more like anti-methods, because a method has multiple arguments and one return, and a pattern has one argument and multiple returns, right? So they really are a complement of each other. So some patterns are so simple that the compiler can generate them for us. Like in the point example, we might have the compiler generate a deconstructor based on the fields. But at some point, things might get complicated enough that we actually have to write some code. Maybe we have to transform from an internal representation to a different representation, Cartesian to polar, or RGB to CMYK, or something like that. So if these things kind of look like methods and we want them to be linked like methods, we'd like to get the benefit of all the other things that methods have, like access control and all of that. So our thesis is, they are kind of like methods. They're just not easily representable as methods. Let's treat them as class members and give them all the treatment that class members get. Now, they could almost be methods. And if you look what other languages have done with some compromises, other languages have managed to turn them into things that look like methods on the JVM. So for example, in Scala, the way you declare a pattern is by writing a method called unapply. And the way they deal with returning multiple things is you box those things into a tuple. And the way they deal with, well, maybe the pattern doesn't match the target, you wrap that in an option. And that's not a terrible way to do it. But one thing you give up on, from that is the ability to overload. You can only have one unapply method because you can't overload methods on return type. Another compromise that you get out of that is a lot of boxing. Primitives get boxed into boxes, values get boxed into tuples, tuples get boxed into an optional, and they've made some progress in reducing the boxing overhead in recent versions, but it's still there's a performance compromise. C# has more tools at their disposal, so they've managed to avoid both of these pitfalls because they have out parameters. So they've modeled deconstructors as extension methods with multiple out parameters. So they don't suffer the overloading problem, they don't suffer the boxing problem. Unfortunately, we don't have out parameters, so we can't play that trick. So the basic limitation that we're bumping our heads up against is a JVM limitation, that a method can take multiple arguments but can only return one thing. And we could cheaply implement patterns as methods if any of the following were true. The JVM supported multiple return. Well, it doesn't do that. The JVM supported unboxed tuples. Nope, doesn't do that either. JVM supported out parameters. That's kind of like multiple return, isn't it? If we had value types, well, we almost have value types, but we'd kind of like to ship this a little sooner than value types. Or we had box elimination that was so awesome that we never worried about boxing anymore. We don't have that yet either. So, or if we just didn't care about performance, unfortunately, we don't have that luxury. So if we had any of those things and the ability to overload and return types, we could model these things as methods. But we don't have those things. So we still want to make some progress, so let's write out some requirements and see if we can figure out how to do this. We want to be able to encode our deconstructors as class members so that we get all the things you get from class members: overloading, access control, reflective access, a clean object model, et cetera. We want invocations of patterns to be mediated by symbolic linkage, and we want to be able to invoke these things without too much boxing. People don't like it when language features create garbage. If there's going to be garbage created, they want to see the letters NEW in the source code, right? They want to own that garbage. So we try not to foist garbage on on our users if we can. So, all right, well, we have basically one magic hammer, right? What is it? Well, of course, it's method handle. So let's grab that and start swinging and see what we can do. Actually, we have two magic hammers. There's the method handle hammer, and there's the computer scientist's best friend, which is another level of indirection hammer. So between the two of these, I think we can do something. So instead of saying a deconstructor is a method that takes the target and deconstructs it, how about if the method were a factory for a deconstructor thingy? Now, this is a trick we've done before, right? How many people recognize this trick? Can you Lambda meta factory? Anybody recognize this trick? Right. So rather than having runtime that creates lambdas for you, we have runtime that links a call site to act as a lambda factory, right? And that trick was a very powerful trick in Lambda. So it worked then. Let's give it a try, see if it works again. So let's model a deconstructor as a tuple of method handles. It's got one to look at the target and say, do you match or not? And that thing returns Boolean. And if that said yes, it has a bunch more method handles that each extract one component, which probably are going to be field accessor method handles. If we do this right, we should be able to avoid all the boxing, and we should also be able to support dynamic linkage with separate compilation and good composability of patterns. So let's see if that works. We can start with an observation, which is, even though some patterns will get very fancy, the common case is going to be very simple. I'm matching against a point. My applicability test is instance of. My extraction of each of the components is a field access. There's no complex computation to determine if you meet the test. There's no overlap between the computation of fetching x and fetching y. That's the happy case that we want to optimize for. We want to make sure that that's really cheap. And then we want to make sure that the less common case, which is a more sophisticated test or having common computation between the components, is something that is reasonable. Okay, so here's an example of the less common case, where if you want to know if something's a power of 2, well, you keep dividing it, and for as long as you keep getting 0 remainder, you keep dividing it until you get down to 1, and you say, yay, it's power of 2. And then, okay, what's the exponent? Oh, damn, I should have been counting as I was dividing, shouldn't I? Right? So that's an example where you'd like to do some pre-computation, where the result of the pre-computation encodes both, yes, I succeeded, and here's the result you want. But that's the uncommon case, right? So let's focus on the common case first. We also, because of separate compilation, need to make sure one can migrate between these cases, where maybe you start out with the default deconstructor, and then you migrate your code over time, you add more complex deconstructor logic, you want to be able to migrate from one to the other. So to support the uncommon case, you generally need at least one word of state that's carried from that first computation, are you a power of 2, to the extraction, well, what are you 2 to the, 2 raised to what? So we call that a carrier. And from a language runtime perspective, we don't care what the type of that carrier is. It could be an int, a tuple, whatever. That's something that should be private to the deconstructor implementation. So we have a couple choices. We could say, well, forget about that. Let's just recompute these things redundantly and hope that most of the time common subexpression elimination saves us from ourselves, and that might actually work. Or we could say we're going to gather intermediate results into a carrier and then pass that on to the next method handle. So here's another example of a computation that has some, that would involve some redundant computation if we just did it sort of the naive way. This is converting RGB color to a CMYK color, where first you have to compute, you have to scale your RGB value, and then you use that to compute K, and then you're going to use K in the computation of each of the CM and Y computations, right? So we could conceivably just do it the dumb way, and there's a good chance the JIT would help us out, but we don't necessarily want to rely on that. Okay, so here's my Strawman example. We say that a deconstructor handle is parameterized by some types. Its target type, what am I deconstructing? And a bunch of types for the bindings. What are the types of each of the things I'm extracting? And then there's also this hidden carrier type of what's the intermediate value that this funnels through while I'm doing the computation. And then I can decompose that into n plus 2 method handles, where n is the number of bindings I have. The first one says, do some pre-computation, which is enough to determine do you match or not, and if so, compute the carrier. The next method handle looks at the target and the carrier and said, well, did it match? That's generally going to be fast. And then each of the component method handles takes the target and the carrier and says, all right, get me the ith component out. In the happy case, the match predicate is just an instance of test, and the component handles are just field accessors. But in the complex case, there may be some state that gets carried through this computation. So I've modeled that with an interface type here. The method handles are the bottom 3 things. There's a function from the target to the carrier. There's a function from the target and the carrier to Boolean to determine if you match. And then there are n functions from target and carrier to the binding variable. And notice also we can sort of encode this as the opposite of a method type. If we kind of squint, where we take a method descriptor and the parameters describe my output variables and the return value describes my target. So, and this turns out to be a useful encoding if you're willing to cheat a little bit. Okay, so now we have to have some way of dynamically linking to one of these things. We can't just declare them as methods because we want to be able to overload them. But how many people here have read John's blog entry called Symbolic Freedom in the VM? Okay, so it's an encoding strategy for addressing the problem that you have strings that you want to encode as VM identifiers that can't necessarily be easily encoded in the VM instruction set. Identifier rules. So we can use this trick. We can say, let's take the name and the descriptor, and let's encode that as a name that the VM can represent. And that's going to be a pretty stable thing, because that's usually what we link against, right, is names and descriptors. So if we encode that using this encoding, you get something a little bit horrible looking as an identifier name, but the user's never going to see that. That's just what goes into the class file. And this becomes a static method that doesn't actually do the deconstruction, but it serves up one of these deconstructor handles, right? So for the matcher that whose types are whose binding variables are int and int, you call this method, you get a deconstructor handle that describes that matcher. And the body of that method, it's just an LDC using constant dynamics, so the thing that comes back is a constant. So that's nice. Okay, what does invoking look like? It's like, well, there's that ugly method, which, like I said, the user's never going to have to see. Compiler writers can deal with it, but we do that kind of stuff. And we have, again, a constant dynamic bootstrap whose arguments are the class name, the name of the deconstructor, and the method type that it's its descriptor. And the bootstrap goes, computes that ugly name, looks to see if there's a method by that name, if so, calls it, and because these deconstructor handles are just constants, we can use a constant dynamic for that as well, so that you don't have to keep fetching that deconstructor in that other class every time you're using it. And the first time you use it, the constant will get resolved, and then thereafter it's just a constant. And then the matching gets translated pretty straightforwardly. You do a load constant of, find me the appropriate deconstructor. I call the preprocess handle. I then pass the result of that to the matches. If that succeeds, great. I call the component 0, I call the component 1, I get the bindings out, and I use them. And in the common happy case, it's carrier free, it's allocation free. I've done all the hard work through constant loads, so I'm not going to do those redundantly every time I match. And in fact, I can push more of this work into the constant pool. The expression that describes the method handles, dc.preprocess and dc component 0, dc component 1, those are constants too. I can use constant dynamic to put those in the constant pool also. So this is going to, you're going to pay a little bit of cost at link time to set this up, and then everything is going to inline beautifully, because what are these method handles? They're instance of and field accessors. So you're going to end up with, when it comes out of the other side of the JIT, you're going to end up with the handwritten code that you would have had, without any additional overhead. So that's nice. All right, let's see some more nice. These things are constant tuple of functions. Because they're constants and functions compose, if we do our job right, destructors can compose also. And this composition can again be done with constant dynamic at link time. So the overhead of doing this, it all becomes a one-time overhead. So, for example, I have a deconstructor whose descriptor is D, and I have a method handle whose descriptor is D. And remember, the descriptor of the deconstructor is really an inverse. I can compose these two things using method handle combinators, and the result is a method handle that takes a T, extracts the components, passes them to the other method handle, and returns whatever that second method handle returned. So if that second method handle were a constructor, then this is my clone operation. And if that second method handle was something that encoded it to a string, this would be a serializer. So the deconstructors compose nicely with other method handles. They also compose nicely with other deconstructors. So you can have more sophisticated patterns like, does this match pattern P and pattern Q? Well, I can write a combinator in about 10 lines of code that takes pattern P, pattern Q as deconstructor handles and produces a new pattern that implements, do you match both of these? And if so, give me the bindings for all the bindings from P and all the bindings for Q. Similarly, I can have a combinator for OR pattern. Do you match this or that? As long as the binding variables have the same names and types. Or in the nesting example, like where I had, are you an add node whose left node is a 0? I can take the constant pattern, 0. I can use a nesting combinator to say, nest the 0 pattern as the first argument of the deconstructor pattern, and it will give me back another deconstructor, which again is all constants, and this will all be done at constant dynamic bootstrap time. So these things, these things compose really nicely, and as a compiler writer, it means I don't have to generate very much code at all. Right? All I have to do is, my source code encodes like an AND pattern, so I generate some bootstrap calls out to the pattern runtime to say, give me the AND pattern, and then all my deconstruction goes through that one same interface that I showed you. So it moves a lot of work from the compiler writer to the language runtime. So that's pretty cool, huh? So that's invoking one pattern. What about invoking a whole bunch of patterns with switch? Ideally, we'd like for our pattern dispatch to be O of 1, not O of n, right? If I'm saying, are you an integer, are you a string, are you a float, are you a double? These are mutually exclusive things. So I should be able to use some kind of hashing strategy to pick one of those without having to ask too many instance of questions. A lot of languages translate switches into long chains of if then else, and our prototype does this too, right? But we'd like to do better. And you end up with something that has O of n time complexity. So what we'd like to do is say, well, let's take this more complex switch, lower it to a switch on integers whose case labels are 1, 2, 3, 4, 5, 6, 7, and then have a selector function, which is an invoke dynamic, that's going to return one of these numbers. And what's the argument list of our invoke dynamic? Well, it's a bunch of pattern constants, which is really cool because patterns are constants. And the argument list of an invoke dynamic bootstrap has to be constants. So I just load my patterns out of the constant pool, pass them to my invoke dynamic selector, which at link time is going to build a decision tree. And then I call that thing and say, well, which one of these might it have been? And it'll say, well, it's definitely not 1, 2, 3, or 4, so start at 5. Right? So there's a whole range of translation options, but of how fancy we get, how much work is done by the bootstrap versus how much work is done by the generated bytecode. So we haven't quite figured out where we're going to land on that, but it's really nice that you can pass a complete description of all your patterns, no matter how complex, to one bootstrap, and it could, if you got fancy enough, just build the decision tree at first invocation time. So here's an example of what I mean. This is the same source code I showed you, at the beginning, where I'm doing a bunch of matches on, are you an int node, are you a add node, are you a negation node? And so, the way I might translate that in the scheme that I just described is, okay, so for each of those case labels, I LDC up one of my destructor handles. And then I lower my switch from being pattern labeled to being int labeled, and I call the selector function that I invoke with invoke dynamic, whose static arguments are the list of all the patterns, and I call it with my target, and it gives me back an int, and then I just switch right into that, and the VM implements table switch really efficiently, so I'm done. So that's pretty cool. All right. What about binary compatibility? Right? When we invoke a method, we want, and the method's in another class, and that other class has been separately compiled. We would like reasonable changes to that method to not break the call site in the client. And we'd like the same thing for pattern invocations, right? So, and we would like to be able to, for example, change the carrier type of the pattern, or go from no carrier to having a carrier, or go from a reference carrier to a value carrier without breaking existing clients, because we don't want to say, gee, if you recompile this class, you have to recompile all those other classes. We don't like to ask people to do that. So this is something we're still working on. Some of these transitions work. Some of these transitions don't quite work yet, and we're bashing our head against that. But I think we'll get there. But this is one of the one of the characteristics that we want to have for this mechanism is the ability to separately compile the pattern specification from the client. So okay, so let me just sum up. This is not just about what we're doing in the Java language. We're putting most of the guts of this in the JDK runtime. This is a trick that we use to great effectiveness for Lambda. When we put Lambda Metafactory in the JDK, very quickly a lot of other compilers, such as Scala, started targeting Lambda Metafactory as their backend, which not only means that they get to use stuff that's already in the JDK that they don't have to reinvent, which is great, but also benefit of interoperability across languages. So we're hoping to play the same trick again, provide a nice runtime for pattern match and dispatch, have it be efficient, have it support binary compatibility across separate compilation, and have that be usable from Java, Scala, whoever wants to use pattern matching. So with that, I think I have a few minutes for questions. Eric, go ahead.
So this component call, do you need dependent types to type that identity? How do you type those?
So the question is the component call. The component method on the destructor handle just returns a function, and that function takes the target type, which is what am I extracting from, and the carrier type, which is just an implementation detail, and returns a strongly typed component. But method handles in the JVM they're strongly dynamically typed, so we don't have to write down their types in the Java type system. You just have to make sure that whoever's calling them and whoever is implementing them agree on what the types are. And since the types of the components come from the source of the pattern, you're saying here's a pattern that yields up an int and an int. The client will generate code that expects an int. The implementation will serve up an int, and the handshake gets done at linkage time. So you don't need dependent types. You just need to be careful, which is the same trick that basically any language using the invoke dynamic or method handle runtime has to put up with. Oh, okay, Remy.
So I have already implementing the pattern matching in a dynamic language that use invoke dynamic. So the problem you have, you will create your whole tree of method handle too soon. So by example, if you have a pattern that need a class, but you don't match it, you don't want to load it. But currently with your tree of constant things, you will load the type too early.
So the concern, which you should bring to the expert group meeting on Thursday, is, well, I've got a pattern that whose components are types A, B, and C, but maybe the client site doesn't need the third component, and we don't want to load class C. Well, first of all, class C will probably have been loaded as a result of loading the class that has the pattern declaration. No, but even if not, let me finish, Remy. Even if not, what the client is going to do is it's going to invoke a deconstructor handle combinator that says, drop the third parameter type. Because it knows that it doesn't want that result, because the source code said, var A, var B, nothing, dropped. And so that method handle will never get invoked. And that type doesn't appear in the class file for the client, so that won't trigger unnecessary class loading. Somebody else gets to ask a question. You can bring those to the expert group meeting.
No.
Andre. No. Remy, please. You get lots of my time to do it. Go ahead, Andre.
Thank you. So what you described depends on constant dynamic, right?
It does. It could be implemented without constant dynamic using invoke dynamic. So the way we do lambda metafactory today is if you have a stateless lambda, which is a lambda that doesn't capture anything, instead of linking the call site to the constructor for the lambda proxy, we invoke the constructor once, and we link the call site to always return this constant. And so you can simulate constant dynamic with invoke dynamic, whose bootstrap links the result to a constant combinator. So we could do this without constant dynamic.
So my question was, so do we have to wait until constant dynamic is there to have this feature or not?
So I hope we're not going to have to wait very long at all for constant dynamic.
Okay.
Yeah, Dave.
Can you speculate on, I know this is foundational technology used for a lot of different languages, hopefully, but can you speculate on the Java syntax?
The syntax for the matching or the declaration of a matcher? So I think it will look a lot like the examples in the early slides here. That's my current thinking here. I'll pull those up. So that a statement switch would look like this, that a expression switch would look like this, and that nested patterns would look like this. That's my current thinking. This will be, this is being discussed on the Amber mailing lists, Amber Dev and Amber Spec Experts. So there's been some examples posted, but that's, if you have thoughts about it, Amber Dev is the place to bring those. So deconstruction is a harder problem. How you would describe a deconstructor is a kind of stuff 10 pounds into a 5-pound bag problem, because you have two argument lists, what's my target and what are my binding parameters, and you have an extra bit of state of, is this a matcher that always succeeds, and that's useful to know, or is this a matcher that might fail? Does it return Boolean or what have you? So it would look something like a method, but its header has a little too much junk in it to qualify as a method. So we're currently exploring various permutations of stuffing 10 pounds into various smaller bags. Yeah. That in a constructor, you're used to saying this dot x equals x, this dot y equals y. The dual of that is x equals this dot x, y equals this dot y, where x and y are the binding variables. And then the question of how they compose, like how you would compose a deconstructor with a super. We're working on that. Not there yet. I don't have pretty examples to show you. I wish I did. So the question is, do you expect to have default constructors? I talked yesterday, I guess it was maybe Monday, at the workshop about data classes, which were a sort of lower ceremony data carrier abstraction where you would automatically get constructor equals hashcode toString and deconstructor. I think there was a question in the back.
Did you think about the partial deconstruction scenario? I want to take 4 fields out of one class, move it to 3 fields on the other class, mostly like data binding scenarios.
So a deconstructor doesn't have to serve up the entire state of the object. Just like you can overload constructors, you can overload deconstructors that have varying numbers of binding parameters. And so you can say, just get me this portion of the state. That's fine. On the client side, you can say, okay, well, I'm calling the deconstructor that serves up 3 ints, but I only care about the first one. So there will be some token, a lot of languages use underscore for the I don't care token. And by saying that, the compiler won't generate code to fetch it. So there's partiality that comes through the declaration of the deconstructor, and you can have multiple overloads. And there's partiality that comes from, yeah, I know I'm calling a deconstructor that returns 3 things, but I only care about one of them, so just give me the one.
And the kind of follow-up question, have you thought about doing it from the outside and not by the implementer of the class. Because a lot of times I'll get the type from a library. I can sometimes go and add stuff to it. And it's much easier to have an external system that goes and does the mapping for me.
Yeah, so the question is, what if I have a class whose author didn't give me a deconstructor, but I know how to get to the state? Well, just as you can write a static factory method to delegate to a constructor like that, you can write a static deconstructor that will delegate to the getters for the various state and serve them up together. So yes. Basically, wherever we have different kinds of methods in the object model, constructor, static methods, instance methods, there are sensible analogs of all of those for deconstructors. If I construct something with a constructor, I expect to be able to deconstruct it with a deconstruction pattern. If I construct it with a static factory method, I should be able to deconstruct it with a static deconstructor. If I construct it with a builder, I should be able to deconstruct it with an unbuilder. There's a very nice duality here. Okay, one more question, Tagir?
Speaking about this simplify sample, shouldn't it have the default branch for the case when nothing matched?
Excellent question. So the question is, your switch here isn't exhaustive, and an expression should be exhaustive. So yes, I could have a default branch, or maybe the compiler can prove exhaustiveness for me. How might the compiler prove exhaustiveness? Well, Karen talked in her talk about access control, she talked about how nestmates enable us to do sealed classes, where a class can say, I am abstract node, and the only subtypes that are permitted are add node, multiply node, negation node, and int node. If the compiler knows that, it can know that this is an exhaustive deconstruction and not force you to write a default method. Now, you still might get extra types through separate compilation, so the compiler would emit a silent default arm, which would throw some exceptions saying, well, something showed up that wasn't one of the choices at compile time, go fix your code, buddy. Which is better than you having to write that stupid default, which you wouldn't do as good a job as the compiler does because you're already mad that you have default. So yes, if the compiler can prove exhaustiveness for you, you don't need a default clause. So last question, Eric.
In Haskell and I think in Scala too, you often want to combine the pattern match with a condition. So you want to match on point x and y, and then x should be larger than y or something. Are you going to extend the syntax for the switch statement as well?
So yeah, so the question is, sometimes it's nice to have guards where you can't quite nest one pattern in another because your guard condition can't be expressed as a pattern, but you want to be able to say, does this thing match this pattern that extracts a string where the string starts with ABC? So that's called a guard. That's pretty easy to do. We think we want to do that. We're going back and forth on the syntax. Unfortunately, the code is never very readable when you do that because you have this you have the pattern and then the guard, and it's not clear where the pattern ends and the consequence begins. But we think we'll probably go there. Yeah.
Then your exhaustiveness check will
Yes, once you have guards, unless your guards are really trivially scrutable, it undermines the compiler's ability to do exhaustiveness checks. But still, if you have a case string s where blah 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 blah, and then you have another case string s that's unconditional, the unconditional string dominates the guarded string, and so if you're doing exhaustiveness analysis by type enumeration, as long as you have an unguarded version of each type, you'll still get there. So, all right, cool. Well, thank you very much.